In this video, now we are going to discuss chapter number 8, Introduction to Probability. First of all, let's define and let's see some of the basic definitions of this probability theory. The first one could be an experiment. It is a process which can be repeated infinitely, having some uh, outcomes or results. These results in probability theory are known as outcomes. Okay, so outcomes are actually the results of an experiment. For example, the experiment could be a coin toss. With this experiment, we are either to have a head or a tail. So coin toss is the experiment and head and tail are the outcomes. And now we define another definition, sample space. It is a set that contains all the possible outcomes of an experiment. Since it is a set, so we represent it with the curly brackets and all the possibilities which may result as an experiment outcome. So those are put to be put in this uh, curly brackets. For example, in the previous case, head and tail, if you just make a set of that, that would be the sample space. Similarly, an experiment could be a rolling of the dice. So we are expecting that either one could occur or two or three or four or five or six. These are the possible outcomes. So this is the set that contains all the possible outcomes. So we label it as S representing the sample space, or in some cases it is represented by the Greek letter xi, which represents the sample space, a set containing all the possible outcomes. And now there is another definition of trial. Performing an experiment that is known as a trial. For example, this rolling of a dice is a trial. Similarly, tossing a coin, that is one of the trials as well. Okay, then for the probability, it is actually a quantitative measure of how likely an event is to happen. Quantitative measure of how likely an event to occur. So, what is an event? An event is actually any subset of sample space. Like, for example, uh, in the case of a coin toss, if I say that the team is going to win if head occurs. So, a subset containing only one outcome had from this sample space, that is an event of that sample space. Similarly, in second example of uh, rolling a dice, if I say that the player is going to win if the face up would be an even number. So 2, 4, 6. Since this is a subset of the sample space, so that is why it is one of the events. So this is known as the event, any subset of the sample space. Okay, with all this, now we would be discussing some of the mm, prob experimental probability or relative frequency probability and or the theoretical probability. Those have a bit of difference, but are used interchangeably. So we would be confining ourselves to this probability. The experimental probability. When an experiment is repeated a number of times and the number of trials are carried out. So this is known as an experimental probability. It has got the mathematical form number of times desired event happens divided by number of trials. This is also sometimes known as the relative frequency. P of A means the probability of event A happening. Like for example, if I can say that event A was my outcome in this 2, 4, and 6. So when I would be calculating probability of A, actually I would be calculating for uh, what is the chance of having any even number faced up in rolling the dice. Okay, so with this, mm, I would be discussing this thing, the probability that an event does not happen. First of all, let me give you a mathematical definition of probability. Probability of an event A is actually the number of are required or favorable outcomes out of the total possible outcomes in the sample space. Like for example, in the previous example of getting a heads, probability of heads, let me apply this same formula on that. Uh, in the sample space, we were having heads or tails. So the number of outcomes was 2. So in the denominator, I'm going to write down 2 for this total possible outcomes. And if the team is going to win having the heads, so heads is just one of the two possible outcomes. So for this, I need to have number of the required or favorable outcomes. So since head was occurring, uh, like head was one of the two outcomes, so I would be writing it down 1 in the numerator. So 1 by 2, that is 0.5. Or in percentages, we can say that 50% chances are uh, to get a heads when we toss a fair coin. Here we have got two more concepts, fair, that is also known as unbiased, and then a biased one. Fair or unbiased means which has equal probabilities of all possible outcomes. all outcomes are equally likely or equally probable. Like in this case, this means the probability of heads is 1 by 2 and probability of tails, that is also 1 by 2. Both are having the same probability. Both are equally likely. So the coin is said to be a fair coin or an unbiased coin. And in parallel to this, when we use the word biased, that means probabilities of all the events or all the outcomes are not the same. In the same example, like if you have got the probability of H is, let's suppose, uh, 0.6, and obviously the probability of tails is going to be 0.4, then their probabilities are not equal. So in that case, we would say that the coin is a biased coin because the possible outcomes do not have equal probabilities. Okay, from this now, 0.6 and 0.4, we proceed towards the probability that an event does not happen. First of all, you should be knowing that probability of an event is having a maximum value of 1 and a minimum value of 0. Any probability is within this range from 0 till 1. So the maximum probability of an event can be 1. When the probability of any event E is 1, we say that that particular event is certain for sure. Like for example, if you say that when you roll a dice once, what is the probability of getting a positive integer less than 7? So since you know that the possible outcomes are either 1 containing 1, 2, 3, 4, 5, 6. So in all of these possibilities, you say, you see that all are positive integers and all are less than 7. So whatever the outcome you would get, either that is 1 or that is 5 or that is 6, it satisfies both of these conditions. So this event is said to be a certain event having a probability of 1. And when an event has probability equals to 0, that event is normally termed as an impossible event. So in this case, you say, what is the probability of getting an 8? Probability of an event getting an 8 when you roll a dice. So obviously its probability is going to be 0. So this event is an impossible event. Similarly, when you say that when you toss a coin, so what is the probability of getting a king face, or you can say, uh, for example, an ace from the cards? Since any coin is, for example, either it is having a heads or the other face is having a tails. So we just refer heads or tails. In the case of this or this, we say that uh, the coin is not going to have any of this outcomes. So that event is going to be having a probability of 0, or that event is going to be an impossible event. Okay, with all this, now I come towards one final thing, that is probability that an event does not happen. When a probability of an event it does not happen, which is denoted by probability of a bar, which is sometimes written as a dash as well. So to calculate that, if you have the probability of that particular event A happening, so when you will subtract that from the total probability 1, you will get the probability of A not happening. Uh, for an example, uh, when I say in the case of uh, the experiment of rolling a dice, what is the probability of getting a number greater than 4? Obviously, uh, for that, the required outcome is going to be containing 5 and 6. Since it has got two possible outcomes, so the probability would be 2 divided by total number of outcomes, which is 6. That is 1 by 3. So when I say that probability of a number which is not greater than 4. Not greater than 4 means I am interested in having 1, 2, 3, or 4. Not greater than 4. So, in that case, I'm interested in uh, these 1, 2, 3, and 4. All these numbers are not greater than 4. So, in that case, if I do it, then numbers which are less than 4, actually less than 4, less than or equal to, if I just do it, greater than or equal to 4. So numbers which are not greater than or equal to 4, not greater than or equal to 4 are the numbers which are lesser than 4, obviously, which are obviously not greater than equal to 4. So the numbers would be 1, 2, 3, and when we would be calculating their probabilities, we can subtract those probabilities from 1. For example, probability of number 5 and 6. So in that case, I would be having these four numbers for number greater than 4. The numbers were 5 and 6, obviously. So for the numbers not greater than 4, so numbers were 1, 2, 3, and 4 itself. So I can say that its probability was 4 by 6, which can also be written as 1 by 2 by 3. So to get this probability of not of A, probability of the numbers which are not greater than 4. I can use this formula 1 minus the probability of the numbers which are actually less than 4. So these are 1, 2, 3, and 4. So I can subtract 1 minus 1 by 3. That is 2 by 3. So I'll get this one. In the same way, for example, if I'm calculating 1 minus this 2 by 3, I can get this 1 by 3. So subtracting one event from one, we can get the other. So this happens like that. Let me give you another example of this. I've got a sample space containing numbers 3, 8, and 9. Three numbers are there. So I say my event is number divisible by 3. So the probability of this event E, which is divisible by 3, is obviously this and this. Two numbers out of three numbers are divisible by 3. So if I need to calculate probability of not of E, so I would subtract 1 minus this probability of E. So that is going to be 1 by 3. Probability of the numbers which are not divisible by 3, that is 1 by 3. And we can see very clearly from this that that is only one number which is not divisible by 3. So if I have calculated, or if I have got this probability, when I would subtract this from 1, I can get this one. Or vice versa, if I've got this probability, subtracting this from 1, I can get the probability of these, or the probability of the numbers which are divisible by 3. Okay. With this now, I start off with exercise 8.1. A six-sided dice is thrown 100 times and the number of 5 appears 14 times. Find the experimental probability of throwing a 5, giving your answer as a fraction in its lowest terms. Okay, in this case, we need to observe that the data that we are given with, it has got some of the uh, values, it has got some of the uh, numbers of different things. So we should be using the formula for the probability to calculate the final answer. As you know, that the probability of an event E is actually the number of required outcomes divided by the total number of outcomes. So we would be using this formula to calculate the answer to question number 1. Okay. The coin was tossed 100 numbers of times. So this is going to be 100 So probability of getting 5 is, since we were having that 5 appeared 14 times. So 14 out of total 100 trials, that is the probability of getting a 5. So we can obviously simplify it to 7s are and to 50s are. So that is going to be your answer, 7 by 50 of probability of getting a 5. Okay. In part B, it is required write your answer to part A as a percentage. For percentage, we need to have denominator to be 0. So let the probability written in this form, which was 14 by 100. So 14 by 100 is actually 0.14. So that is the answer of writing the probability as a percentage. In this case, that was 14 by 100. That means 0.14%. This is in percentage. 14% or 0.14. You can have it like this. Either it is 0.14 or 14%. Okay. Then it is question number 2. The diagram shows a spinner that is divided into exactly 8 equal sectors, which are labeled to be 1, 2, 3, up till 8. Rayan spins the spinner 260 times and records the results in a table. Number 1 that occurred 33 times. Frequency tells us the number of occurrence of a particular number in this case. 2 occurred 38 times and so on. Calculate the experimental probability of spinning the number 3. Okay. 3 occurred 26 times. So you can write it down as 26 divided by total number of spins was 260. So this can be cancelled out to give us 26 ones are, and this is tens are. So 1 by 10 is its answer. Okay, now it is part B, the number 5. 5 was got 39 times. So you can have probability of getting 5 is equal to 39 out of 260. This can also be simplified to give us 3 ones are and 3 threes are. And no, instead of this, I can cancel it out on the table of 13. 13 threes are and 13 2 are 26 and 0. 3 by 20. That's its answer. Okay, for part C, an odd number. Okay, how many odd numbers are there? 1, 3, 5, 7. 4 odd numbers. So probability of getting odd number, actually we need to have probability of getting 1, 3, 5, and 7. Okay. 1 was occurring actually 33 times. 3 was occurring 26 times. 5 is occurring 39 times. And 7 is occurring 33 times. So we would add all of them and divide them with the total possible outcomes, which was 260. So adding them up, we get 33 plus 33, that is 66 plus 39, which is 105, plus 26, which is 131. So we can have 131 divided by 260. The probability, this is the probability of an odd number, 131 divided by 260. Okay, now in part D, a factor of 8. When it is said the factor of 8, okay, factors of 8 are, if I label it as F8, the numbers which divide 8 are 1, 2, 4, and 8 itself. Okay, now 1 is occurring 33 times, 2 is occurring 38 times, 4 is occurring 35 times, and 8 is occurring 35 times. So we can have 35 plus 35, 70, 70 plus 33, which is 103, and then plus 38. So it totals to 141. That is our total number of required or favorable outcomes. So the probability of getting F8 factor of 8, that is 141 divided by the total outcomes, which is 260. So that is the answer to part D. Okay, then it is question number 3. A consumer organization carried out tests to find the average lifetime of a new brand of solar lamp. The results of the tests are summarized in the table. Lifetime of lamp, which is given in hours represented by L, and its frequency, number of times, number of the bulbs actually. Okay. There were 30 bulbs whose lifespan was within first 1,000 hours, and there were 75 bulbs, lamps, whose lifespan was beyond 1,000 hours but lesser than 2,000 hours. Similarly, 160 lamps were in the range 2,000 till 3,000, lesser than 3,000, and 35 lamps were whose lifespan was greater than or equal to 3,000 hours. Okay, now calculate the relative frequency of a lamp lasting for less than 3,000 hours. Okay, if you see these are 160 lamps which are lasting between 2,000 and 3,000 hours. But when we are asking about less than 3,000 hours, probability of the lamps having lifespan less than 3,000 hours. With that, the lamps which are within this range or within this range are also included in this. So we can have 30 for this one plus 75 for this one, because these lamps are also having a lifespan which is obviously less than 3,000. So we are including them in our favorable outcomes, and then plus 160 for this. Adding them up, you get 190 plus 75, which is 265. Okay. This is now for the total possible outcomes. We need to obviously add all these frequency values. So adding them up, we get 30 plus 75, which is 105, plus 160, 265, plus 35, which is 300. Okay. Now, for this, you need to include this part as well. The lifespan should be greater than 1000. For that, I'm going to exclude this one. If it would have been just this thing, so we would have added all of these. So that's why their answer would have been 265 divided by 300. But in this case, since we are given with the other restriction, which are more than 1000, for more than 1000, we need to include only this one and this one. So we need to exclude this one. So that's why for this, I need to skip this one. So let me have this one as written like this. 3000, but greater than 1000. So within this range, for that, I need to subtract 30 from this as well. So that would give me 235 divided by 300. So having it all together, 1000 less than or equal to L less than 3000. We need to have their probabilities. So we need to add only these two. 75 plus 160, that is 235. And the total number of lamps was 300. So dividing it by 300. So that would give me, if I simplify it in a decimal, that is going to be 0.783. Okay, now in part B, if a hardware chain ordered 2000 of these lamps, how many would you expect to last for more than 3000 hours? More than 3000 hours are to be uh, having a frequency of 35. So we would be dealing it like that. So let's see for part B. Probability of the lamps having lifespan more than 3000 hours. Obviously, we have got 35 of them out of total 300. And since a sample of 2000 lamps was taken, so that would give us 233 lamps, or the probability is going to be like this: 233 out of 2000 lamps. Okay, now we proceed to question number 4. A survey was carried out where people were asked to choose their favorite type of film from five categories. The bar chart shows the results. This is the frequency along the y-axis, telling the number of people who liked a particular type of film. Okay. How many people took part in the survey? For this, we can see that this bar is between 12 and 16. Let me tell you that if this is 4, uh, a division that contains 4 uh, divisions in it. So this is again containing 4. In between this 12 and 16, it is going to be 14. This is 28. It is 20. This is again uh, this is the mid of this, which is 6. So this is representing lesser than that, which is 5. So same goes with this one. This represents 13. So adding them up, we can have the total number of people, which is 14 plus 28 plus 20 plus 5 and plus 13, which is 80. So 14 plus 28 plus 20 plus 5 plus 13, that is 80 people took part in the survey. Okay, another person joins the group and is asked the same question. Estimate the probability that the person chooses adventure type of the film. This one. So probability that he likes adventure. Since from the previous case, 28 people liked adventure type of films out of total 80. So simplifying them, 4 sevens are 28 and 4 20s are 7 by 20. That means for every 20 people, 7 people are liking adventure. So there are 7 out of 20 chances that the new person is going to like an adventure type of a film. Or you can also say that, for example, if there is another bunch of 20 people who have been asked which type of film they like, so out of those 20, 7 people are expected to reply that they like adventure type of the film. So this is what the probability means actually. Okay, now part C. The survey was carried out in a village with a total population of 480. If everyone in the village was asked the question, estimate the number of people that would choose horror. Okay, for horror, the probability, the number of people watching or liking horror type of film, that is 5. So the probability of horror would be 5 divided by 80, which is 1 by 16 out of total 80 people. So when the population of the village was 480, so I need to multiply this with that, which is 480. So now I can simplify it. 480 divided by 16. So 16 ones are and 16 30s are. So the probability is going to be 30, or you can say that 30 people out of total 480 would be expected to uh, say that horror film is their favorite type. Okay, now it is question number 5. Research shows that the probability of a person being right-handed is 0.77. How many left-handed people would you expect in a population of this much? So this is a straightforward question. This could be done like 0.77 times 25,000. Okay, that would give us the number of uh, right-handed people, and when you would subtract them from 25,000, we can have the number of left-handed people. So this could be the use of that thing. So obviously doing it like this, probability of the right-handed ones are this, which is 19250. So probability of the left-handers is going to be 1 minus probability of R. That means 1 minus 19250, which is 5750 people out of 25,000 are expected to be left-handed. Okay. Now it is question number 6. A flower enthusiast collects 385 examples of a polynomials mathematicus flower in Peru. Just 5 of the flowers were blue. Okay. One flower is chosen at random. Find the probability that it is blue. Just 5 of the flowers were blue. Total were 385. Okay. So this is going to be probability of blue is 5 by 385. You can cancel them up. 5 ones are 5, 5 7s are 35, and 5 7 are 35. So 1 by 77. Okay, now part B. It is not blue. Using that rule once again, probability of not blue is actually 1 minus probability of blue. That means 1 minus 1 by 77. So that would be 76 divided by 77. Okay. Now it's question number 7. A bag contains 9 equal sized balls. 4 of the balls are blue and the remaining balls are red. So that means red are 5. What is the probability that when a ball is taken from the bag, it is blue? Probability of a blue ball is 4 divided by total balls are 9. Like you may understand it, 4 blue and 5 red. So that would give you 4 by 9. Okay, for part B, it is red. Red were 5, so its probability is going to be 5 by 9. It is neither blue nor red. Since all the balls are either blue or red, no ball is other than blue or red. So probability that the ball is neither blue nor red, that is 0 divided by 9, that is 0. And then it is either blue or red. So if you pick up this ball, that is either a blue or a red. If you pick up this ball, this is also either a blue or a red. Or if you pick up this blue or any other ball from this, that is going to fulfill this criteria that either it is going to be a blue or a red. So all 9 balls fulfill this condition. So its probability is going to be 9 by 9, that is 1. So you can say for part C, probability of neither blue nor red, that is 0 by 9, which is 0. And for probability in part D, probability either blue or red, that is 9 by 9, which is 1. So as we were discussing, this is the certain event and this is going to be the impossible event. Like it is impossible to choose a ball from this bag which is neither blue nor red. And this is for sure that any ball chosen from this bag would either be a blue or a red colored ball. So I hope I have made this concept clear. In question number 8 now, a bag contains 36 balls. The probability that a ball chosen at random is blue is 1 by 4. How many blue balls are there in the bag? Probability of blue, that is 1 by 4. And total balls were 36. So out of these 36, I need to multiply it with 36 so that I can get 4 9 is 36. So probability of blue was actually 1 by 4th. So the number of blue balls is actually that I can expect, that is 9. 9 are blue balls. Okay. In question number 9, Liu shuffles an ordinary pack of 52 playing cards. If he draws a single card at random, find probability that the card is a king. Okay. That means, as you know, that for this, we have got numbered cards from 2, 3, 4, 5, 6, 7, 8, 9, and 10. Let me not write this as a solution of this. Actually, I'm just going to explain it at the moment. 4 cards are ace cards in that deck of 52 playing cards. And let me write it here. Then king, queen, jack, and so these are 1, 10 cards, and then king, queen, and jack. So this is a suit of cards. 13 are these. Let me have them for diamonds. Similarly, we have got the same 13 cards for hearts, and then for spades, and then for this. So 13 for this, 13 for this, 13 for this. So that makes it 13 plus 13 plus 13 plus 13, that is 52 playing cards. So the card is a king. So one king would be from this suit, one would be from this suit, and one would be from this suit. So all together, these are four. So this answer, question number 9, part A, this can be solved as 4 probability of getting a king is actually 4 out of 52. So simplifying them, we can have 13. So 1 by 13. Okay, for spades, since that is a suit containing 13 cards, so you can have for part B a spade card that could be 13 out of 52. So that can be simplified as 30 ones are or 13 fours are. So the probability is going to be 1 by 4. And a black card. A black card, so these are these black cards, which is 13 plus 13 divided by 52. That is 26 by 52, which is 1 by 2. 26 ones are and 26 twos are 52. So half of the cards are black and half of the cards are red. That's why. And for part D, a prime numbered card. Okay. 3 is a prime number. 2 is also a prime number. 5 is a prime number. 7. That's it. So 1, 2, 3, 4. 4 from this, 4 from this, 4 from this, and 4 from this. So probability of a prime card is going to be 4 times 4. That is 16 divided by 52. 4 fours are 16 and 4 ones are 4. 4 threes are 4 by 13. Prime numbered card. 1, 2, 3, and 4. These are the cards which are prime numbered. 2, 3, 5, and 7. 4 cards from each type of the suit. So, I'm sorry, I've got this one thing. Uh, One thing that was 4 times 4, 1, then for this, and for this. 4, 4 are 16 divided by 52. 4 by 13. Okay, that's question number 9.